Hello everyone, welcome back. In this lecture, we will discuss a mixed boundary value problem for the wave equation in a spatial domain. The idea is again to obtain a solution in an explicit form, and it will be very similar to the one-dimensional case we did in the first part of this course, where we obtained a solution of the wave equation on a finite interval with the prescribed boundary conditions at the end of the interval, either Dirichlet boundary condition or Neumann boundary condition, and the solution was written in terms of an infinite series involving trigonometric functions. So the idea is similar, and in this lecture we consider a two-dimensional wave equation. Okay, so let's again let me describe the mixed problem in generality. Okay, so again consider the wave equation now in a bounded domain, bounded smooth domain, omega in Rn, and in some finite t interval. Okay, so with prescribed initial conditions, and say 0 Dirichlet boundary condition on the boundary of omega. Okay, so in this generality, it is not at all possible to obtain a solution in an explicit form unless this we make some assumptions on the domain omega and the initial conditions, etc. Okay. However, one can develop a general theory of existence, uniqueness, and we can also obtain estimates on the solution in terms of the initial data and even boundary data. It need not be zero, we can prescribe some other non-zero boundary condition. But when we develop a theory, then we not necessarily restrict our attention to wave equation, and more generally will develop a theory for general second order hyperbolic equations. And that will take us into the modern theory of the subject. So we have now developed in this course. So you can see there are so many things one need to do to go further in this study of PDEs. Okay, so it's not at all possible to obtain all the time the solutions in explicit form. So one has to develop a general theory of existence, uniqueness, and the related topics. Okay, so in this lecture, the topic of discussion is a 2D wave equation, and this is the case of uniformly stretched uniform membrane. Okay, so this assume that membrane is placed in the xy plane. So for the derivation of the equation, this membrane can be of any shape, but later on we'll consider circular membranes where it is possible to obtain the solution in explicit form in certain cases. Okay, So the physical situation is that a uniform tension T, okay, that T denotes uniform tension per unit length over the boundary of the membrane, okay, and sigma is the density of the membrane. So since it's two dimensional, here density means mass per unit area, okay, and the oscillations or displacements are taking in the z direction, and that is denoted by u when this membrane is held under this uniform tension, okay, and again one applies the Newton's second law, uh, etc. So if you are interested how these equations are derived, so you should consult a book on physics, especially theoretical physics, so where these equations are derived from first principles, okay, and then this displacement satisfy the two-dimensional wave equation, and of course in deriving this equation several assumptions on u are made. Only small displacement, otherwise this c will not be a constant, just like the vibration of a string, that's one dimensional wave equation which we derived in the first part of this course, very similar to that, okay. So here it's two-dimensional wave equation, okay, and this speed of propagation is given by c square equal to t by sigma. So these are the uh, physically relevant uh, quantities, this t and sigma. This is uniform tension and sigma is the density of the membrane, okay. And in polar coordinates, so this, if we use this x equal to r cos theta and y equal to r sin theta, this equation becomes, okay, so I'm just writing this Laplacian, okay, this is in rectangular coordinates, and that becomes, okay, let me again remind you, this change of coordinates into the rectangular to polar coordinates is singular at r equal to 0. So while seeking solutions in the polar coordinates, one should uh, consider only those solutions which are bounded as r tends to 0, okay. So we make some more assumptions, okay. So this capital F denotes external forces, if any, okay. Uh, so we make some more assumptions in the problem. So we assume that membrane vibrates freely, that is there are no external forces, so that F is 0, and I also assume that the motion is symmetric about the origin, that same thing as saying u is independent of this angular variable theta, okay. So in that case, with these two assumptions, the problem becomes very simple. So this is again a second order equation only in two variables now, t and r. So theta is removed there, okay, and the initial conditions become u of r0 equal to phi of r, u sub t r0 equal to psi of r, and that is for 0 less than r less than a, where a is the radius of the membrane, okay, circular membrane we are assuming that. So circular membrane of radius a, okay, and u equal to 0, so this is one boundary condition. So physically this means the membrane is held fixed along the its boundary, okay. So that's what this means, okay. Okay, now we proceed to obtain some special solutions of this equation, and these are called normal modes of vibration. So here is a small definition of normal mode. So a normal mode of vibration is one in which all the particles of the system with are with same period and pass through their mean positions simultaneously. Okay, so they might have different amplitudes, but they are all periodic. So mathematically, this means we are looking for a solution in the form of separation of variables. So u of rt is r of r. So even with respect to time, it is just a trigonometric function. So we take that as cos omega t minus epsilon. Okay, so these are the normal modes. Okay, so r is only a function of r. Okay, now you substitute this form of the solution in the given equation, namely this one. Okay, so then that simplifies to, so we get an ordinary differential equation for capital R. Okay, and that is, so you just cancel this cosine term that appears everywhere here. Okay, so you just get only uh, an equation only in terms of R. Okay, and that equation is d square r by dr square plus 1 by r dr by dr plus omega square by c square r. Okay, so this omega is the frequency. Okay, r period. So if you, that 2 pi by omega is the period. Okay, and epsilon is something positive. So that also we'll see that we can express both in terms of cosine and sine. Okay, so this one again, okay, this some simple change of variable, so this can be reduced to Bessel. So we come across this Bessel function many situations in this course. Okay, and since we are looking for a solution which remains bounded as r tends to 0, that I commented earlier also. So this r equal to 0 is a singularity, so we should be careful that. Okay, and the only solution is the constant multiple of this j0. So again, let me recall. So j0 is Bessel function of order 0 and of first kind. So there is another solution that's also called Bessel function of order 0, that's y0, but that has a logarithmic singularity as r goes to 0. So in this present case, that is rejected. Otherwise you will have two linearly independent solutions of that equation, Bessel's equation. So it's not function, it is equation. So this Bessel's equation has two linearly independent solutions, but the other one is rejected for the reason it is unbounded as r goes to 0. Okay, so that's a required solution. Okay, where a is an arbitrary constant. Okay, so in order to satisfy the boundary condition, so we have this boundary condition u equal to 0 at r equal to a. Okay, so that is transformed into this r of a is 0. So this if you transform this condition on J0, so you must have this J0 omega A by C equal to 0. Okay, so this condition must be true. Okay, so that way this omega cannot be completely arbitrary. Okay, so it has to be. So this A is again coming from the problem, so that's radius of the membrane, and C is also coming from the problem, so that is speed of propagation. Okay, but we already know that the Bessel function has an infinite number of zeros, so that's okay. So this information we already have regarding the Bessel function of J0. Okay, so it has an infinite number of positive roots. Okay, and also they tend to infinity. Okay, so they are not bounded at all. So this omega A by C has to be one of these roots, because this condition must be satisfied, and that fixes the periods or frequencies. Okay, this omega k, so you have to have only this omega k, and write that. So C alpha k by, so k equal to 1. Okay, so in this uh, normal mode, so this frequency or uh, period is given by this infinite sequence and not arbitrary omega. Okay, so that's what we get. Okay, so now you denote this by u1, u2, uk, all these uh, successive normal modes, k equal to 1, 2, etc. So namely uk is ak, so ak's are arbitrary constants, j0 alpha k r by a cos omega t minus epsilon k. Okay, and since the equation is a linear equation, okay, this is linear equation, so we can use the principle of superposition. So in general we obtain a solution of that equation as an infinite series. Okay, provided the series converges, and we can verify this term by term differentiation is possible and other things. Okay, so assume all those things, and by expanding this cosine function we can also write this, so just use cosine rule here, so this becomes ak cosine omega t plus bk sine omega t. Okay, so this ak and this ak are not same. Okay, I'm just taking this one, and so you get some constants. Okay, and what about the initial conditions? So this is just we obtained a solution satisfying the boundary condition, and what about the initial conditions? Okay, so now consider the initial conditions, u equal to pi r and ut equal to psi r, and since this is general solution, okay, so we just plug in t equal to 0 there, and try to see if phi and psi are represented again as in the power series, and hopefully we'll be able to obtain relations for AK and BK. Okay, so AK here, AK and BK are arbitrary constants. Okay. Okay, so now you just simply substitute t equal to 0 there, so this will produce only AK, and that is 0, and the left hand side is phi of r. So we get phi of r is equal to ak j0 alpha k r by a. And similarly, if you differentiate with respect to t, okay, and this will be a sine function, and when I put t equal to 0, that vanishes. So only this bk term comes, but now when I differentiate, there will be a omega k. Okay, and that's what I have written here. So psi of r is equal to omega k bk j0 alpha k r by a. Okay. So in order to determine this ak and bk, now we'll make use of some orthogonal properties satisfied by this Bessel function. Okay, I will again repeat that. Okay, so just to make everything uh, suitable for the application of that orthogonal property, we make change of variable here. So we put x equal to r by a. Okay, this. So remember, this 0 is r less than. Okay, and then with this change of variable, so the x belongs to 0 1, and now you substitute r equal to ax in this expression. So we have phi of ax equal to ak j0 alpha kx, so that r by a is replaced by x, and similarly psi of ax is omega k bk j0 alpha kx. Okay, the orthogonal properties, this I uh, again repeat. Okay, so this, if you consider this family of j0 alpha kx, so k equal to 1 to infinity, so the orthogonal properties of this family of functions is that this 0 to 1 x j0 alpha kx into j0 alpha lx dx is 0 if k is not equal. Okay, and when k is equal to l is equal to k, this is expressed in terms of this Bessel function of order 1 if l. So let me write that in separate. Okay, so these are very similar to the orthogonal properties enjoyed by the trigonometric functions. The only difference now is there is a weight x. Okay, there is a weight x here. That's the only difference. Okay, and that will help us in determining this coefficients ak and bk. So for example, here in order to determine ak, so you multiply both sides by j0 alpha kx, and again multiply by x, and you just integrate over 0 1. Okay, so here on the right hand side all the terms will be 0 except that particular k, and that determines this ak. Ak comes with this coefficient, so when you divide by that, so you get that. Okay, so this the determination of these coefficients is straightforward owing to these orthogonal properties enjoyed by this family of Bessel functions. Okay, this J0 alpha kx. Okay, alpha k's are the positive roots of the J0. Okay, so we obtain the coefficients ak and omega kbk, and hence this omega k are already determined. Okay, so now we get this akbk, and now once you substitute again here, so you just substitute ak and bk, so we'll have a solution with these conditions. Okay, so these are referred to as again, okay, this Fourier Bessel expansion. So given any uh, orthogonal family, okay, so we can always expand any general function in terms of those members of the orthogonal family, and that's what we are doing it. Okay, so what remains to be done is, okay, so after obtaining the solution in this infinite series, so we have to worry about convergence, and then, so that is the first one, and this term by term differentiation. So then only we can say that it's a required solution. If you are not able to do that, it is just a formula. Okay, and also we want this u to be c2, at least c2. Okay, so we have already seen in the case of wave equation in one dimensions, generally we require more smoothness on the initial conditions in order to uh, prove that u is a C2 function and term by term differentiation is possible. Okay, so here also similar conditions need to be assumed on these initial conditions in order to show that u is indeed a C2 function and term by term differentiation is possible. So u is indeed a C2 solution of the given equation. So I am just omitting those tedious calculations, but you should do that carefully. Then only it is a real solution. Okay, so just obtaining a formula for the solution in an infinite series and leaving these verifications unchecked, and that's not a good idea. So we have to do this checking, okay, that u is indeed a solution, and we can differentiate term by term in this infinite series and show that u is indeed the solution of the given equation. Okay, so please do that. Okay, so obtain some sufficient conditions on the initial conditions so that this is a C2 solution, and with some exercises, so you can also try that, and then I will close that. So for example, here you take a simple function, so phi of r equal to some constant times a square minus r square. So this is just vanishes at r equal to a. Okay, so this condition, and you take psi equal to 0 and verify that this formula makes sense in the sense that so u is a C2 function and term by term differentiation is possible, everything. So this is a very nice function, right? Just it's a polynomial in R, so it's smooth, etc. Okay, so you have to only find out what this AK and BK. BKs are all 0 because psi is 0, so BKs are 0, so there are no BKs, only AK. So for that again you require some knowledge about this Bessel functions. Okay, that's one exercise. And another exercise, so from the beginning you have taken this external force to be 0, okay, and now you take the external force to be a periodic function of time only. Okay, so you just take the external force and you can take just initial data 0, okay, and again obtain a solution. So these are the exercises. Obtain the solution. Okay, and here also just so very simple forcing term, so it's a periodic in time. Okay, so and see what changes you need to make in obtaining the this normal modes and this power series. Just see how it changes. Okay, so that's an exercise. Okay, so with that one simple example, so we close the discussion on this mixed problem. Uh, so in general, it's not possible to obtain solutions in explicit form. One has to do more analysis. Okay, thank you.